Okay, so today we're going to move to the last part of the class, which is on MPI, and there's going to be a homework 5 on MPI, and also, as we discussed, this will be part of the final project in terms of implementing the deep neural network. So just a brief introduction. So obviously, from a programming standpoint, the shared memory is the easier platform. Okay, you can have any process can read and write to the memory locations. So there's no explicit communications you have to worry about. So it simplifies a lot the programming. But as you can imagine, there's no sort of magic. Still, data needs to be moved around and so on. And so essentially, you're asking the operating system to be responsible for data movement and coherence. So for example, if a processor makes a change to a memory location, and then let's say does a write, and then another thread wants to read, then you need to make sure that the write is sort of visible to the process that's doing the read. So in principle, that sounds pretty straightforward, but things get very complicated once you say, well, actually, when you're writing data to a memory location, you're not necessarily writing to memory. You're typically only writing to cache, okay, or maybe even register, okay, because it's very expensive to go to memory. Okay, and if you every read and write goes to main memory, it's very, very slow. So you're going to start using this cache, and so now things become a lot more complicated, right? Because when you say, when was the last update to this memory location, where is the data, and so on, it becomes quite complicated. So operating systems are quite good at that, but definitely it's very difficult to maintain this coherence in the memory, and making sure that essentially the results are correct, and that essentially every write by a thread is visible by other threads when they're doing a read, and so on and so forth. So there's a limit to essentially, not necessarily a limit on the size of the memory, it's really a limit on how many cores are allowed to read and write to this memory, okay? And so the more scalable approach, which sort of puts the burden on the programmer, is to then declare that you're going to have computer nodes that are sort of independent, okay? So they're connected by a network, but a process can only read and write to its own memory, okay? If you want to read and write to another memory location or memory owned by another process, it's not possible, and there's going to be a different mechanism to do this, and it's essentially managed by the user rather than say the operating system. Okay, and so the advantage of this approach, it allows you to build much larger computers with a very, very large number of processors, and the hardware to implement the solution is significantly simplified. Okay? So process can no longer read and write to another processor's memory, but obviously they still need to exchange data. Okay? So if a processor does some computation and produces some numbers, typically these numbers are going to be needed by another processor to continue the calculation. And so how can we make this happen? So this is the sort of solution proposed by MPI, this concept of message. So essentially a message is some memory location, so essentially an address and number of bytes from that, starting from that address. So this is a sequence, a contiguous sequence in memory, okay, that say one process has in its memory P0, and then say you want to send this data to processor 1, so you're going to take this chunk of memory, essentially put it over a network, okay, so communicated through the network and then written at the end on the receiving node in some memory location on, say, processor P1, for example. Okay? So you exchange these messages, which is basically consists in a send and a receive. But the trick is that the user now needs to explicitly do that. Okay? So essentially, if another process needs some data, then when you write the program, you need to explicitly say, well, send this array, this address from this process to that process, and so on. And this consists of a pair of send and receive. Okay? So there are many ways to do this, but the standard is MPI. So MPI is so it's an API. Okay, it's a standard again that defines various functions in the API, how they behave, and so on. And then they're implemented by different vendors, libraries, and so on. So MPI, so this de facto standard for distributed memory computing. It's the focus is on high performance, high efficiency. So it's become very popular model. So MPI is message passing interface. So here I'm going to take a little bit of a sort of a break. It's not really super important for this class to understand this taxonomy, but it's very, very common, and a lot of people refer to it. So might as well briefly discuss that. So we have this this vocabulary, and we understand these different concepts. But if you look at the computer architectures, okay, and the way the computers are organized, so you have different types of sort of canonical organizations that are used and that correspond to sort of different constraint or different purpose. So we've already seen in CUDA so-called SIMT, so this is single instruction, multiple threads. Okay, and on CUDA, this specifically corresponds to the fact that so essentially the threads are not individually keeping track of their instructions. Okay, instead you have a scheduler that issues one instruction for, let's say, warp. Okay, and all the threads in the warp are going to execute this instruction. So there's simultaneously this concept of threads, okay, which are have some independence, have some resources and so on, but they're sort of tied together by the fact that they're all executing the same instruction at the same time. Okay, so this is single instruction, multiple threads. Now you have a slightly closely related concepts, which is SIMD, which came actually before this SIMT. So SIMT is really connected to GPUs and so on. So SIMD is sort of a concept that came, that was there before, and it's sort of very closely connected. So it's single instruction, multiple data. So it kind of does a little bit the same thing, but you no longer have this concept of thread. Okay, and in practice, it means that on the multi-core processor, you have these vector capabilities. Okay, to do sort of media processing to play movies, videos, sound, and so on. And so it has the ability to perform. The processor has the ability to perform short vector operations. And so, for example, you have operations like doing additions, doing multiplications. Okay. And the input is a vector, let's say size 4, 8, and so on, and the output is going to be correspondingly a vector. Okay, and so you have multiple units that are performing the same operation, but on different data. Okay, so it's very close to the previous one, except that here you don't really have this concept of thread, right? It's just a unit that's going to do a certain calculation, whereas in CUDA, you do have this concept of threads, and threads have resources allocated to them and so on, so it's, there's a slight difference here. But the SIMD was sort of the older concept, and basically corresponds to these vector operations. Okay. Then, we've actually, this is something that we've already seen, so multiple instruction, multiple data. So essentially, this corresponds more to the concept of multi-core threads, okay, where you have different units that essentially execute different functions and on different data. Okay, so it's multiple instruction, multiple data. So it's basically what happens on a multi-core processor. So you may have one process with many threads, okay, but all the threads are sort of doing different things. Okay, so it's much more flexible model compared to the GPU model. Okay, and so typically you have much fewer threads in this case, but they can do completely independent things. Okay, they just run different functions, different. It's part of the same program, but different functions. Okay, and so finally, you have many more of these four-letter acronyms, but this is sort of the one that's going to be relevant for us today. So single program, multiple data. Okay, single program, multiple data, and so this is essentially the MPI model. So the idea now is you're going to have multiple nodes, so essentially multiple computers or processors. And each processor is going to run the same. They're all going to run the same program. Okay, so essentially you're going to have multiple processes that are running. Okay, so it's a little bit like logging on different nodes and then just starting the same program. So every time you start a program, you start a process on that node. So you have all these processes or programs that run concurrently, and then but they're part of this sort of pool of processes that are allowed or this capability of communicating through the MPI library. Okay, so it's a little confusing that everybody's running the same program, but as we've seen previously, it's the same idea as before. So everybody's running the same program, but every process is assigned a unique ID or rank, okay, from 0 to n-1, and so based on this rank, you're going to do different operations. Okay, so for example, if you're processing a grid, you're going to split your grid into subdomains, and process I is going to compute subdomain I. Or if you're doing IJ matrix, then process P may take care of the IJ block in the matrix, okay, based on the rank. Okay, and the communication is therefore exchanging data or bytes through a network, but this is done explicitly in your computer program. So essentially the user needs to specify exactly what how these communications are happening. So this is roughly kind of an outline of what a typical MPI program would looks like. And so there are certain constraints. So here I'm just going to give you a brief introduction, and then next week we'll sort of go into more of the details. But so here you assume you have 4 cores. Okay, everybody's running actually the same program, but again, because everybody has a unique rank or ID, they are going to take different paths through the program, or at the very least, they're going to work on different data. And then to exchange data, to send data from core 0 to core 1, you're going to call MPI send and MPI receive. Okay, so it's so-called two-sided communication in the sense that there is a send and a receive. You need this pair, send-receive pair. And the reason why this is the case is, well, the send might be somewhat clear. Okay, well, this process, the data is ready. Some data is ready, has been computed, is available, and you're going to be sending it over the network. Okay, so you can do a send. What's happening with the receive is just essentially, at some level, a very practical thing, which is that imagine you're sending a big array. Let's say it takes a gigabyte of memory. Well, clearly you need to have some memory location to store it. Okay, you need to allocate memory, so you need to provide a memory address that's allocated and ready to be used, for this communication. And if you think about it, it's more than just, having allocated memory, but essentially it should be an area that, for example, you're not currently working on. You don't have live data that you're using in your calculation because it's going to be overwritten by the communication. Okay, so you need to specify a holding area, a pointer, and then essentially sort of leave it free while MPI is doing the communication and writing in that memory location, and at some point MPI will say I'm complete, and now the data is there and can be used. Okay, so there are various constraints that need to sort of happen for these communications to be done correctly. So on the send side, the data needs to be ready, okay, it needs to be computed, so this happens at a certain point in the program. And then on the receive side, well, then the space needs to be available and sort of free to be written upon, okay, and then once the receive completes, then this program here can continue and make use of that data. Okay, so it's called two-sided communication, and each side is actually rather important. And there is a more recent version of MPI, that MPI 2, which has one-sided communications. And when you think about one-sided, it sounds great. Oh wow, I can just send data over there, no need to do a receive. But it's actually a little bit misleading because there's no magic. Okay, if there's no receive, it means that somehow that there's some space available on the receiving node. Okay, so in some context, it is possible to have this type of guarantee, but in general, this is not possible. Okay, so this is really for certain types of calculations only that this one-sided communication makes sense. In general, you do need two-sided communication, in order to make sure that the resources are available and so on in terms of memory for this communication to happen. Okay, so let's go ahead and let's look at our first MPI program. So like I said, MPI is a standard. So you have many, many vendors, libraries, and so on that offer MPI implementations. So these are the most common. So OpenMPI might be the somewhat of a standard, or it's very commonly used. So OpenMPI is the one we use for Google Cloud. Okay, so you have the link here, and then there is this mpic and mpic. And there's also some Cray MPI libraries, Intel libraries. There's a Microsoft MPI library. So you have a bunch of libraries that sort of implement this the MPI, the API from of MPI. So this is actually quite complicated to be done because the whole problem is understanding the network of the computer and the network capabilities of the computer. So, it's actually quite difficult to design a library that can be installed on a computer. Will figure out what sort of network, like how the nodes are connected to each other, and so on. And then based on that, figure out a good way to perform the communications. So there are lots of technical details that are rather complicated to get this correctly. Okay, so now just like OpenMP and so on, this is a very, very portable. So it's MPI can be installed on any computer. You can run it on your multi-core computer. Okay, you don't actually need multiple computers. Okay, so if you run on your laptop, you will see multiple processes starting on your computer. And these processes, in principle, are not allowed to exchange data. Okay, so they cannot read and write to each other's memory. Okay, they're different processes. So their sort of memory is protected, but they can exchange data through MPI. Okay, which is a sort of a different process. Okay, and then obviously you can do this on GCP, and then on computer clusters. On many platforms. So here I want to make a short note. This is not like super important, but that it's when you're doing cloud computing, you get access to this virtual hardware, and this is sort of the power of cloud computing, that you get this sort of generic hardware that has well-defined capabilities. You can install Ubuntu. You can install the CUDA libraries, you have MPI and so on. So for example, when you allocate for the project, it will look like a shared memory computer. Maybe you can, I think, create instances with up to 96 cores on one node. Okay, and it all looks just like you have 96 threads or cores with shared memory. Okay, and you have this concept of virtual CPU, which is basically one thread. So actually, for example, a typical core can do hyper-threading, can run 2 threads at the same time. So for example, if you request 2 virtual CPUs, you may actually just get a single core, and with 2 threads, 2 hyperthreads on this core. Okay. So the point is, so you have this sort of instances you can create. Okay, and when you start your instance, some resources are allocated in the cloud and so on, and the system is such that you don't really know the actual underlying hardware that you're running on. Okay, so typically it will be just one node. Okay, it will be one node. It may be a single processor, or it may be a couple of processors on different sockets on the same motherboard. But it may actually be even, you're using one thread from this processor over here, one thread from that processor over there. I mean, it could be a fairly complicated, setup, because it depends on the sort of software they're running to do the virtualization. Okay, so you always do the same, but the underlying hardware, how this is implemented physically, may change. And if you log out and log back, if you stop your instance and restart it, you will get something different. And typically, we're not saying this too much. At least, hopefully, we won't see that in the projects. But for example, when you look at performance, you can get surprises, right? Because especially if we start allocating, requesting a lot of nodes, because you really don't know how fast the network is, right? On the regular high-performance cluster, you have a very fast, dedicated network. You know that you're going to get compute nodes, on that network and so on. But in cloud computing, not the case. Okay, so it could be actually between your nodes. There may be a slow network. It could be very far away. Probably not, but who knows? So there's a lot more variety of hardware, and so things are a little bit less fixed and sort of known compared to a regular high-performance cluster. Okay, so in terms of compiler, well, it's just MPI C++. So essentially just a regular C++ compiler, but then a couple of libraries to compile the code. And then you have the header, mpi.h. Okay. So another element that is a little complicated is that now starting your program is obviously more complicated. It's not just running your program. It's not just going to command line and launching your program, because this would only start your program would just start one process, like on the node you're logged on. Okay. So if you want to, imagine you have 128 nodes. You want to start your program. Well, you have to start 128 processes. So it's basically the equivalent of logging on each node and then starting your program on every single node. This gets obviously very cumbersome real quick. So there's a command, mpi run, that essentially takes care, based on a list of hosts or computers that can be used to run the program, will start your code and run it on all the nodes. So typically there is some underlying infrastructure that helps MPI run, for example, figure out what are the available hosts that can be used for computing, and how to choose them and assign them to your calculation and so on. So in our case, it's very simple. When you log on GCP, you have a certain number of CPU cores available, and MPI run will just start. For example, if you have 8 cores, then it will, or 8 threads, it will just start 8 copies of your program. So you get 8 processes running. And then similarly, you need to handle situations where one of the process fails. Okay, so maybe everybody terminates. Okay, that's fine. But it's very possible that there's a bug in your program, or in fact there will be bugs in your program, and so one of the nodes, one of the process dies. Okay, well then you need to pay attention and stop everybody else, right? Because MPI is designed in a way that if one node dies, essentially the calculation cannot proceed. Okay, it's very sensitive to failures. So you can imagine that if a node dies, and for example, you were sending it data, or you were expecting data from that node, and so on, your program would not be able to run if that node dies. So MPI run, or the MPI library, detects when a node has stopped running, and then we'll just terminate all the other nodes. Okay. So in fact, if there is a bug and your program crashes, then MPI will terminate all the other nodes, and there's a special MPI finalize command in your program that happens at the end, which will ensure sort of a smooth termination if your program successfully completes. Okay, so for example, here is what you get running this. So start from here, we're just on GCP, so just do make. Okay, so make file does MPI C++, gonna create this executable, MPI pi send, MPI hello, and here I'm showing you how to run MPI hello with, so MPI, you say MPI run -n8, so this means that you're gonna run your program 8 times. So you're going to create 8 processes. So actually, the number of processes you're creating is maybe different from the number of cores. Okay, so you can MPI run -n2, even if you have many cores. And similarly, I can say n16, n32, or n64. Okay, then you will have multiple processes assigned essentially per core. And as before, you have the operating system that manages all these processes and tries to kind of schedule them on the available resources. Okay, so this is the output of the program. Hello from task so and so, from 0 to 7. Then one process, is going to print all the number of MPI tasks that are running and so on. Okay, and then you have these error messages. So I'm going to talk a little bit about this. It's not super important really, but I wonder what's happening with this thing. So it says that it's unable to find any relevant network interfaces for so-called open fabrics, which is OpenIB. Okay, and so it's telling you that another transport is going to be used, although this may result in lower performance. So that sounds pretty bad. Well, I can disable this warning. Okay. And then here it says that basically many processes are kind of giving you out this message, so it's kind of sparing you just telling you it's the same things happening on the nodes and so on. So okay, so this is sort of a a more technical thing, but I want to briefly explain this. It kind of shows you also the complexity of this. So you have network is a complicated thing. I definitely don't know the ins and outs of network technology and network software, but suffice to say that there are many different pieces of hardware and essentially protocols or libraries that can be used to communicate. Okay, and some are low performance, some are high performance. So the high performance obviously are very expensive, but they will give you much better communication. And in fact, in a given network, you may have several protocols that are sort of working at the same time. Okay, so actually MPI may have different channels that it uses for communication at the same time. Okay, so you have so you can refer to here documentation. You have this, so you have many transport layers. So essentially, it's a combination of the software and the hardware that's used to actually exchange data and perform various optimizations during this communication. So, for example, these are example of InfiniBand is, for example, is a very fast, very fast network. And then you have others like Portals 4 and so on. So you also have protocols that are associated with shared memory, only available on shared memory nodes, so you can play with that a little bit. And then you have TCP sockets. So TCP is sort of the, if you wish, more or less universal standard for communication between computers. So TCP sockets are basically always available. This is sort of the default standard channel for communications between computers in a network. So TCP socket is always available. InfiniBand, for example, this requires you to purchase a special card for your network interface. Okay, you need a special card in your computer and a special network, like switches and so on, that supports the InfiniBand standard and so on. And so it's both the standard and the hardware, and it's high performance. Okay, and so this OpenIB. So basically, what it's saying is, it sounds like kind of a weird message, but it's actually very important. Because typically MPI, again, is a high-performance interface, okay? And it's going to be used in high-performance clusters. And most high-performance clusters support, these very fast networks, like InfiniBand and so on. Okay, they spend a lot of money to get this fast network. And so, in fact, MPI sort of will expect that, this InfiniBand, for example, is sort of available, or there's some sort of fast interconnect you can use for communication. So the warning is just telling you that you seem to have a lousy cluster. Okay, is that okay? And the underlying assumption is actually you have spent your money on the good cluster, on the good network, but there's a bug in your program and you're not able to use it. Okay, and then you want to go back and fix it so you can actually get the performance that you paid for. So that's what the warning is basically about. And so here, because we are on the cloud computing, there is in fact no fast network. It's just a TCP network, okay, or a virtual version of it or whatever. So hence, we don't have access to this. So here I'm just going to skip, but you may want to at some point, look into that because if you want to really get good performance and so on and understand a little bit what's happening, it can be good to look at the options that are supported by your MPI library. So if you have this OMPI info, so this is again for OpenMPI, will give you a lot of information about essentially the way the library was implemented, all the options that are available, so hopefully you can tune it for the computer at hand. So the BTL is the option where we have to look at. So this is basically this is the option that specifies, how to perform these transfers. We call byte transfer layers. So this is basically the lowest sort of level of communication between. So it's called point-to-point, so between two nodes in the network. And then you have MTL and KML and so on, which are sort of high-level, options that do, more advanced, have more advanced features, but we don't really need that right now. So just BTL. And so, for example, right now in OpenMPI, so it's actually not that complicated. You have these different options. So, like I mentioned, TCP is sort of the default. This is what we're going to be using. And Vader, okay, kind of a strange name or whatever. Vader and SM, so shared memory, are protocols that are specifically for shared memory. So, meaning that if two processes are, on the same node, and they try to communicate through MPI, MPI will be able to use something, well, it basically doesn't use TCP because you're on the same node, so it will use some other mechanism for communication on the same node. So basically, the communication now is just a memory copy, okay, and then you can use libraries to have processes kind of exchange data, with shared memory, when they share memory. Okay, so it's basically just a mem copy between processes, and this can be done with this Vader and SM. Okay, and that's OpenIB is high performance, and then the TCP. Okay. So now, all right. So after all this speech, what's the final message? Well, okay. So the final message is, well, you can run without any option, get the warnings. I mean, it doesn't really change anything except you get the warnings. But if you want to get rid of the warning, you can either specify, that you want to use TCP itself. Okay, this is good. Or easier is just to say, well, use all transport layers that are available, but just keep OpenIB because I now know that this is not available on this machine, and then it will use essentially the other ones to do the communication. Okay. All right, so let's close this note and continue. All right, so let's look at our first program, MPI hello. So the option, so I mentioned this, -n, also -np, same thing. It's used to determine the number of processes, okay? So you can click on program here, but I don't think you can do that. Just show you the code here. So this is what a typical MPI code looks like. I mean, a very, very simple one. So very, very basic. So, but essentially, it's mostly interesting how you start and how you end. We'll look a little bit what goes on in the middle later on. So first, you always have MPI init and MPI finalize. Okay. So MPI init essentially. So again, you're running a program on one node, so you need to be aware of how many nodes are involved in this calculation, and how is it that you're going to be able to communicate with them. Okay, so this is this MPI init, okay, that tries to kind of set everything up so that all these communications can happen and can happen efficiently. And then at the end, you do MPI finalize. Okay, and when you reach this, it means that your calculation essentially is complete. So, for example, if the process continues and ends, then so that process dies. But MPI will not throw a fit and kill everybody else, because you will say, okay, well, that process just finished normally the program, so now we're fine. We just need to wait for the other process to finish as well. Okay. So MPI finalize sort of declares that, okay, if you reach this point, then everything is normal, and if this process dies, it's kind of okay. It's just because we're done with the program here. And then so you have MPI com size. So now you're going to have a lot of MPI functions of this type, which allow you to call into MPI. So for example, MPI com size. So com is communicator, size of communicator. So communicator is basically simply the set of all processes that are able to communicate with MPI. It's called the communicator. And MPI com world is the sort of default communicator. It's basically the communicator of all nodes in this calculation. And we'll see later on that in some cases, you want to create subgroups of processes. Okay, so smaller groups of processes, and create communicators associated with these subgroups, and so there's going to be something something else than MPI com world that will show up. But right now, just MPI com world meaning all the processes. Okay, and so here just ask the MPI library, well, how many processes are in MPI com world? So essentially, total number of processes involved in this calculation. And then MPI, so the rank is basically the ID of each process. So it goes from 0 to n minus 1. Okay, it's called a rank in MPI com rank. Okay, then you can have stuff like get processor name, kind of useless, but well, it can be used mostly for debugging, or when you want to print messages or write to a file. So actually, writing to a file, for example, is this can be important. Because if you want to debug your program or somehow print stuff to a file, you have to be a little careful, because if you write to a certain file, well, all the processes, everybody's running the same program. So presumably all the processes are just going to write to the same file. Okay, so that's going to be confusion. Everything's going to be sort of entangled or mingled. So here, for example, you may query what's the host name, okay, and then based on this, create a file with a special name and write to it. Okay, so all right. So let's look at a program that's a little bit more complicated. So computing pi using MPI, and so okay, here is the screenshot when you're running the code. Okay, so I'm running on four processes here, MPI pi send. Okay, so I'm starting all these tasks, so essentially here, this is the classical demo for pi, where you just throw a random dart. So basically you pick a random point on the unit square, and then you look, whether you are inside the unit circle or outside, and this probability will converge to pi. Probability converges to what is it? Pi r squared divided by 4 or something. So you can extract pi from this average, and so here, what I'm doing is simply starting 4 processes, and each process they start with its own random seed, and then generating a random sequence. Okay, so everybody has different random seeds. So everybody gets, its own statistics, like how many samples were in, how many samples were out, and then essentially you just average out all these statistics on a single node, and this gives you an approximation of pi. So it's convergence is basically 1 over square root of n, where n is the number of samples, so it's quite slow, but it kind of converges more or less. So let's see. Let's see what goes in the code now. So you can. So if you want to go online, this is on GitHub, but I'm just going to show you the pieces of code here. So actually, this code here is. So immediately you're going to see that MPI is it's fairly simple conceptually, but in terms of writing the code, it's sort of verbose and a little bit tedious. So for example here, imagine so you have all the processes that are throwing these darts or generating these random numbers, and everybody has their own estimation of pi. Okay, they look at how many random points were inside the unit circle. Okay, so everybody computed my pi. Okay, and now you need to take all these statistics from say these 4 nodes, and again you need to do some sort of reduction. Okay, so now this is more complicated. You cannot just take my pi and just add all of them together. Now you need to explicitly send that result over the network to one node, the master node, and then the master node is going to do this reduction. So this is a very classical sort of setup in MPI, where you say if my rank is so and so, then do this, and otherwise do something else. Okay, and so this code kind of shows up all over the place. And so typically in send receive, it's almost required to do that, because clearly in send receive it's not symmetric. Somebody needs to send, and the other guy needs to receive. There's an if send, then call MPI send. If receive, call MPI receive. Okay, so you can see that the if statements are going to multiply in the code, but there's no real way around that. I mean, a couple of things that can be done to avoid that, but to a large extent, that's what it is. So here, for example, everybody sends to node 0 or master node. So you say if rank is not master, then do a send, and if rank is master, so that here, you will do a receive. Okay. All right. So let's look at the MPI send. So MPI send. So like I said, the standard is very simple because it's going to be completely generic. So the way the send works is you give an address, okay? You give a memory address, and then essentially you specify, how many elements should be sent over the network, starting from this address, and you need to specify the type. Okay? So I'll come down to that. So this is the buffer, number of elements, the type, destination of the target process. So the communication, so this is just, essentially when, you're here specifying the rank of the target process, but the rank is defined only in the context of a specific communicator, right? If you look at the subsets and so on, then, within the subset, you may have a different rank. So you specify the rank and the communicator together, and that uniquely define a specific process. And then there is a tag. So tag is, so we'll see how to use it, but in some cases, it may be useful to just sort of receive messages, and for example, you don't specify which source the message is coming from, or you're sort of generically waiting for a message to arrive, and then you may want to use a tag to be able to essentially distinguish messages. So this is what we're going to be doing here. Okay, so since everybody's falling asleep, let's ask a question. What is the point of MPI data type? why are we specifying MPI data type? Actually, let me just show you all the types that are available, so that there is no surprise here. You have car, int, long, unsigned, float, double, bool, complex, double complex, W, car, bytes, pack, well, byte. So for example, you have an MPI byte. Well, MPI byte is, like the name indicates, it is a bytes of a sequence of bytes. So a sequence of bytes or bits, okay, just a binary representation. You're going to send that over the network, fine. So why is it that we need to specify the data types? What?
So you know how much data you're sending?
Well, more or less, right? Because for example, the int, that's 4 bytes. Okay, the float is 4 bytes, the double is 8 bytes. So you know how many bytes, right? I mean, it's like when you do the could copy, there's actually no data type. Right? You just give an address, and you say, size of the type times, number of elements, and you're done with that. So, okay. So any idea?
I think typically in GPU there are integer processing units and double processing, floating point processing unit. Kind of we have to tell MPI which type so that the system know which kind of maybe integer processing units or floating point processing units.
Sure. Now, of course, you need to have type information. But for example, you can have an array of int, an array of double, and it is legit to just take the beginning address and just write whatever sequence of bits you want, right? Without specifying the type. For example, you can have an array of integers, another array of integers, and do memcopy. Okay, the memcopy doesn't care what's the type, it just copies the bits. That's all. The types is just something that the compiler essentially uses for correct code execution, and indeed some of the assembly instructions, do depend on types, but when you copy, it's just bits. Okay, so I guess nobody knows the answer.
Go back to the slides so maybe they can read it, like read the documentation again.
You mean this one here?
Yeah, so just people can read the
Right.
actual function code.
Yeah, so basically okay, well, the question is what is a float? Okay, what is a float? So do you guys remember what a float is?
So you're assigning to a float notation number and then the next one
Right.
assigned to it.
Okay, exactly. So you have this mantissa, exponent, and sign bit. Okay, you have these 2 pieces of information. Okay, and although the standard kind of defines exactly the range of everything and so on. For example, just say the sign bit. The standard doesn't say whether the first bit should be the sign or maybe the last bit should be the sign. Or do you store the exponent then the mantissa, or the mantissa then the exponent, or even, for example, the mantissa, like what's the order for the bits? I mean, it could be any order you want. So the problem is when you write the MPI library, you have to be very careful that you're now running on different computers. They might even be running, so the hardware is different, the operating system might be different, and everything might be completely different. Okay, so the way numbers are presented could be different. Okay, so on regular clusters, usually all the nodes are sort of identical. They run the same operating system and so on. So everything is the same. But in general, this is not the case. So for correctness, you have to specify the type. For example, if a float is defined differently, on 2 different processors, then MPI will have to actually do a lot of bit manipulation for the numbers to match on both ends. So you're talking essentially about the same floating point number, but with different representations. Okay, so it's actually very tricky. And so you need to be careful that, if you send byte, this may work on some processors, but not necessarily for all of them. Okay, so let's look at the second part. So here, if rank is not master, so here I just sort of cut the first bit. And so now if rank is master, you take the else branch, this is the second half of this program, and now you have MPI receive. Okay, so what's happening is, see, the way this is working is master is node 0, n equals 0. So you're going to be waiting for all other processes from 1 to n minus 1, okay, receiving this number, okay, again the type. And here the way things are done is I'm saying MPI any source, okay. So the problem with the MPI is that MPI very often leads to programs where there's a lot of synchronization points, okay, and sort of spurious synchronization points. For example, here, if you process 0, you're waiting for n minus 1 numbers, you know, in your calculation. Okay, and for example, the order in which the numbers are arriving is irrelevant. Okay, it doesn't matter. Like whichever is the first one to arrive, that's all good. Okay, so you can write your program such that here, for example, you specify, oh, it should come from process 1 or process 2, 3, and so on. Okay, and then your MPI will just wait until data from process 1 arrives and will not proceed further until this happens. Okay, so for example, if process 2 sends first, then just wait. Okay? You have to wait for 1 to arrive. So here I used a special keyword, MPI any source, okay, which allows to say, well, from whatever source the message is arriving from, it's going to sort of satisfy this receive. It's going to be matched, that send is going to be matched with that receive as a successful receive. Okay. And so now, actually, I'm going to use the tag because what's happening is, so I'm computing pi, so I'm generating the statistics, but I'm doing this over several rounds, right? If you go back to the output, right? So go these rounds. So initially you had 2 million throws, so divided by 4, so whatever, maybe it's 500,000 per process. Okay, everybody does 500,000, so you get 2 million, and then this is first round, and then you iterate the next round, you get 4 million, and then 6, 8, 10, and so on, you know, until you have all these rounds. And so if I say MPI any source, right? Right. If I say MPI any source, you have to be careful because, you know, I could start mixing up the rounds together. So the tag actually contains the round information. Okay. So essentially, this loop is going to go to keep going. Okay. So you have tag equal I. This loop is going to get going until essentially you've received n minus 1 messages with, say, at the beginning tag 0. Okay, and that finishes the first round. And now you go to the next round. You're now waiting for n minus 1 messages with tag 1, which is next round, and then tag 2, and so on. Okay, and so now the way the program runs now is kind of interesting. Every round, the messages, you know, arrive in different orders, and they're processed, you know, in whatever order they're arriving. But you make sure that data from different rounds are not mixed together. Okay. At some level, of course, it doesn't matter because everything being random, you could actually mix the rounds. But you know, there's definitely some cases where, you know, mixing the rounds would be an error, and so this avoids that. Okay, so basically, you know, this is the syntax for MPI receive. Same thing as before: message, count, data type, source. Now you have this extra tag, and I'm sorry, the tag was there before, and then you have this extra status. And the status is something that can be used, for example, if you use these wildcards like MPI any source and so on. Then you can use status to figure out what was the source. If you're interested in that, or if somehow the source is important, you can use status to query information about this MPI receive. In case some of the things here were, you know, sort of wildcards. Okay, so this is the overall program, and so you can see now how, you know, tag equal I. So I'm sending to process 1 with tag I, and here I have MPI any source with the same tag I. Okay, so I'm going to be matching the send and receive in this fashion. So it's very important for correctness. It's essential that all the sends are matched with a corresponding receive. Okay, so here the send is going to be defined by, you know, the type, the length, and so on, the tag and the com, and then it has to match, you know, the receive. So the receive needs to have the same type, same length. So here, actually this is going to match any source, okay? And obviously it needs to have the same COM and the same type, okay? So every send needs to be matched with corresponding receive, otherwise the code will just hang, okay? If you have a send, but nobody ever does the corresponding receive, then it hangs, and vice versa. If you do receive, there's no send, then again it will hang and be stopped there, okay? So that's a bug in the program. So you have to make sure that all sends have a matching receive, and in particular the sort of signature or the type of the message has to exactly match the type that's in MPI send. Okay? So each send must be matched by a corresponding receive. There's also the question of order. And of course everything happens asynchronously and so on, and the network can do really strange things. So in principle it may be possible for messages to arrive in different orders. Okay, like you can send message 1, message 2, but somehow message 2 arrives before message 1. Okay, that's weird, but it actually may very well happen. For example, if message 1 is 1 gigabyte and message 2 is sent immediately after and it's just 1 byte, it's very possible that the byte actually arrives before message 1 is complete. Okay, but the MPI library guarantees that the messages are received in the same order they were sent. Okay, so essentially, even though the data may arrive first, MPI will pretend that the communication is not complete yet because there was a message before that that's still being processed. Okay, so the order is sort of enforced. Okay, until message 1 is done, MPI will not say message 2 is ready. Okay, so the order is maintained so that, for example, if you're doing your receives and so on, or if you're testing for communications, you know exactly the order in which the messages are arriving. You know that this exactly matches the order in which they were sent. So since it's the same program, obviously you can determine completely, you know completely ahead of time, what these orders are and so on, and you can make sure that your program is correct. Okay, so this is basically saying the same thing, but if sender sends 2 messages of the same type, one after the other, then the MPI runtime ensures that the first message is received first, meaning that the communication will complete first. So we'll see next week that this concept of completing a communication is actually a bit subtle. So here, the way I explain, you have MPI receive, and it's so-called blocking, that essentially the code just waits until that completes, so then it's kind of clear. But you also have non-blocking send and receive, where essentially you can test whether the data has arrived, and if not, you can continue, do something else, and come back to test the status of the communication. Okay, and then in that case, this concept of completion, becomes a little bit, a little bit more complicated. Okay, so let's talk about. There are a number of things I need to cover for the final project. The most important thing is collective communication, so this is what I'm going to talk about now. Now for the homework, there's actually a number of concepts and communicators and so on that I need to cover, so I'll have to postpone that to next week. So you talk about communicators, groups, and so on. But at least for the final project, everything, you only need collective communication, so I'm going to try to cover that today. Okay, so collective communication are very important. So what we talked about so far is point-to-point. So basically, process 0 sending data to process 1. So it's called point-to-point. So one node to another node. So of course, at some abstract level, that's all you need. I mean, that's all that can ever happen in network anyways. Data going from one node to another node. Okay. So some network sort of may support broadcasting and more advanced operations, but typically, that this point-to-point is the basic sort of building block. But we've seen that there are certain operations where this point-to-point is not sufficient. So, for example, if I want to do a reduction, okay, something that we've seen before, but here it's kind of interpreted in a slightly different context. Let's say you do a reduction. Well, you could have all processes say send data to node 0. but actually this is not an efficient way of doing things, okay? And the reason is as follows, that essentially the network, you can think of it, the network as basically roads that, you know, or transport or wires that, you know, connect different nodes together, okay? And so the basic problem is there's a finite number of wires, you know, available, okay? And so if everybody just sends directly its reduction data to node 0, then there's a huge bottleneck at node 0, right? Node 0 is going to receive a huge flood of data, and let's say there's only one wire coming in, it's just going to be very, very slow. And if you think about it, that makes no sense, because for example, let's say you want to reduce n numbers, ideally, node 0 you know, may only receive a couple of numbers, and then do a final addition, and that's it. Okay? There should be a better way than receiving all the n numbers all together at node 0. So of course we're familiar with this. This is the classical tree reduction, but now it's not about you know, sort of leveraging the compute capability. It's about leveraging the network, the communication capabilities. Okay? So imagine node 0. You want to minimize the bandwidth that's at node 0. So let's say at node 0 is doing the left branch here, so it's going to be receiving 2 numbers, then receiving another number, then receiving another number. Okay, so only 3 numbers. And essentially, there's a lot of communication happening, but on these other nodes that are essentially using other parts of the network, other wires and so on, and it can be done independently. So that overall, the bandwidth appears to be much higher because, you know, you're using more fully your network. Okay. So essentially, this is you know, what this is all about. So you know, you have this. So apparently, this is the Los Angeles highway. Pretty impressive. So basically, you know, you want to use all the wires, or all the highways, all the lanes available. Okay, and if you tell the cars that they should all take exactly the same road, okay, gigantic gridlock. Okay, so you want the traffic to kind of distribute as much as possible throughout all the communication highways, and essentially this is what. So when you do these collective operations, this is essentially the problem. Okay, you want to move data around, and you have certain network topology, so you have certain highways available, and the question is how do you route the information through that network in order to complete this operation as quickly as possible. Okay, so this is a very complicated business, and maybe not always done you know, very, very well, because it's very, very complicated. So obviously, you can, for a given topology or a given system of highway, you can definitely, you know, figure out what's optimal. But it's much more difficult to have a library that is sort of optimized for sort of general configurations. But what's happening is, you know, so communications are complicated. They depend on the network topology. But the good thing is, essentially, there are relatively few of these communications. So for example, we always keep talking about you know, reduction or scan, and then there is broadcast and so on. So there's a number of basic operations that keep being reused over and over again. So there's, you know, more than 10 of them or whatever. And so MPI has special function calls for that, you know, for these collective operations, and hopefully they're reasonably optimized for the platform that you have. Okay. So let's review these functions. So first one is MPI broadcast. Okay, I'm just going to go quickly over these different functions now. So first one is MPI broadcast. So MPI broadcast basically means that a process has a piece of information, okay, this green square, and then it needs to send this green square to all the other processes. Okay, so typically the way this works is process 0 may read data from file, or may, you know, request an input from the user. Okay, gets an information, and then it's going to send information to all the other processes, so they know what to do. Okay, so much more common actually is the sort of dual or reverse operation, which is the reduce. Okay, so everybody has a piece of information, okay, and you want to add all these numbers together and just get one number. So for example, if you want to calculate a dot product, or again, if you do a matrix vector product or dot product of two vectors, then it's a sum, and you can do local sums. In the end, each process has just one number, and those need to be added together to just get the final number. So it's a reduction, and this shows up when calculating norms, errors, linear algebra, lots of situations where you have a reduce. So reduce can be done with many types of operators. Okay, so essentially all operators that are commutative and associative, can be used as reduction operators. So we've already seen that. So you have max, min, sum, product, all the logical operations. And then also maxlock and minlock. This is kind of an MPI thing, but it's very useful. So maxlock and minlock allow you to do a reduction on essentially two things. Let's say an integer and another number or tag that's attached to this integer. Okay, so this allows you, for example, doing a max. Let's say doing a max. So the max itself is the reduction operation, but then you may want to know what was the location of this max. Okay, the index, for example, the rank that contained the max or whatever, some information that was attached to that number. So maxlock is going to do the reduction max on the first number, and then the second number is just sort of attached to it and can be queried later on to get additional information. So I'll show you an example. Okay, so here's an example with again this MPI prime, and now looking at doing this reduction. Okay, I'm sorry, it's not right. MPI, sorry, yeah, MPI prime. Previous example was pi. So here it's a little different. We're essentially going to have each process essentially calculate, how many primes are in some interval, okay, and then counting. So basically counting the number of primes, and then maybe looking at the largest one they have found. Okay, so you imagine you have an interval from 0 to n-1. You're going to split this interval, let's say, into 4 parts. So each process is going to compute, one part. Okay, so you have my start. This is limit is just how many primes you want to do, and then you have a certain stride. Okay, so that everybody's is testing different integers n, and then you're asking, is it prime? Then if yes, then count it, and then you just keep the largest. And then you want to look at the total number of primes that were found. So you do MPI reduce. You're sending PC and storing the result here. This is an int. The reduction operation is a sum, and the result will be stored on this node. Okay, and then here similar reduction, but doing a maximum. So now we want to find the largest. So this is the largest that process I has found, but you want to find the largest overall. So you do a max reduction and put the result on node master. Okay. Okay, so we're kind of running out of time, but if you're interested, you can click on this link. This is actually nothing to do with MPI, but it's pretty cool. So it's showing you, how to visualize prime numbers by looking at multiples. So I'll just spend a couple minutes. So essentially, each line here represents essentially a multiple. So the first line is just going around every one, but then the next line is going around, every even, so multiples of 2. And then there's no line for multiples of 3s, another line for multiples of 4, another line for multiple of 5. And so if you look at a number, the number of incoming lines is basically the number of factors that you have in a given number. And so if you have only 2 lines, then these are prime numbers, because that's the 1 and then the number itself. Okay? And if you have more than 2 lines, then it's a number that's not prime. And then you have this concept of perfect numbers. What's perfect numbers? Perfect number is a number when you look at all its divisors and you sum them up together, you get back exactly the same number. Okay, for example, 6 works like that. 1, 2, 3. Right? If you add up all the factors, you get back 6. That's a perfect number. 28 is not a perfect number. And so you can play around with this and look at the numbers that are perfect and so on. And if you're into it, you can even scroll to the right and get these crazy looking plots. Where you can see, it's kind of interesting to see those that have a lot of lines incoming. For example, that guy, there's a huge number of factors in it. Anyways, so it's just a side comment. Okay. All right, and so just to wrap it up, so now you have the gather operation, where basically everybody has a piece of data. It's going to be gathered on one node. And then you have the corresponding scatter operation, where a node has different pieces of data, and then each piece gets sent to a different node. So, for example, in your final project, okay, you're going to have rank 0, who's going to read all the data, all the images from file. Okay, so it's going to have all the images. So in one of the implementations, you want to split this data set into subsets of images and send each subset to a different process. Well, this is exactly an MPI scatter operation. Okay. And then you have the reverse, which is sort of MPI all gather. Everybody has partial data, and you want to gather everything on all the numbers on every node. And so another thing that you need for the final project is MPI all reduce. So MPI all reduce is basically a reduce. So you're going to take these 3 pieces of information, add them together. The difference with reduce is everybody has the result at the end. Okay? Instead of reducing onto just one node, you're doing the reduction and then sending a copy over to all the nodes. So, for example, when you're computing the gradient, okay, when you're computing the gradient, okay, as you remember, everybody gets a fraction of this sum. So, for example, if you have 4 processes, everybody gets a quarter of this sum. Okay, but then you want to apply the gradient, so you've got to sum across all 4 nodes to have the partial gradients, and then all the nodes need the result for the gradient. So it's exactly an all reduce. Okay, everybody has a partial gradient. You add all these gradients together, and then all processes need to have this gradient available, and you can update the neural network coefficients. So it's an MPI all reduce. Okay, so you have another example, proc mean value, which does that. So proc mean value basically does this min log. So each process has a bunch of integers. Each process is going to compute its minimum. So for example, 839, and then you're going to take a minimum across all the processes, and then send the result to all ranks. Okay, so this is basically reduce. Only one rank has the lowest value. Here, all ranks have the same value, this minimum. So this is an all reduce, and this is basically what it looks like. Just MPI all reduce. And I mentioned this min log. This is an example of min log. So the way min log works is you have local array and global array. So you're going to take the minimum, but you want to also know where which process owned the minimum, had the minimum. So the way you do this is you create an array of ints. Okay, the first entry is the actual value minimum, and the second entry is rank, or whatever number you want to attach here. Okay, so you do this, local res 0, local res 1. Now you do MPI min log. Result is written here, and so global res, by definition, the first entry will be the actual minimum that was found, okay, according to this reduction operator. And then the second entry is going to be the rank that was attached to the minimum that was found. Okay. And you also have the MPI toInt as a special type, because these guys are in twos, right? They have 2 ins. This is needed for MPI and minlock. Okay, and then last thing is all-to-all. So this one is sort of a matrix transpose, if you wish. So here, each process has like 3 numbers, and then these numbers are going to be shuffled. So if you think about it, it's basically the same as taking a matrix and saying, well, when you start, each process has a given row in the matrix, and after the all-to-all, each process has a given column in the matrix. It's sort of a transpose operation. So for example, 0 is going to have all these guys, the first one. 1 will have all the guys in the middle, and 2 will have the guys at the end. Okay? All right, so very quick, introduction to MPI, how to use MPI, point-to-point communication, and collective operations. And so, well, there's a lot more to cover. So this is essentially sufficient to do the final project now. But in terms of homework 5, there's quite a bit to cover. So we'll do that next week. Okay, thank you.